Yeah, thank you. Okay, so, well, first of all, thank you for being here and during this presentation after the lunch, and thank you for the invitation. It is nice today because we have this alternation between theory and theoretical works, and I'm going to present something that is again from the out of equilibrium physics stream of works. And there won't be any neuron, unfortunately. I will be most interested in learning and in behavioral data. And in particular, I'm interested in learning in curriculum learning. So this is what the talk is about. There will be some human experiments, but this will go to be mostly about neural networks. All right. Okay. So the first thing is, okay, what is curriculum learning? And I like to start with this simple example. If there is some music educated among you, you may not be scared by this music script. Myself, instead, I'm not educated in music, and this is quite threatening. However, my claim is that the reason why people can afford reading something like this is that they started from something as simple as this one, which is definitely less intimidating. This is a general trend in human and animal learning, starting from simple problems and progressively increase difficulty until you become an expert. If I present you the problem that is expert level, you will fail. And so we have, despite this is something that has been known for almost forever in the scientific literature, it never appeared. There are some examples of a German book of people training dogs where they talk about curriculum in the late 800s, but there is nothing in the scientific literature. So the first example comes with Pavlov, where among the methods that he describes in his book, we show that if you train dogs with curriculum in visual discrimination tasks, they perform better. But this is not the subject of the analysis. I guess Skinner is another example. Skinner worked with many animals. He famously taught pigeons to play bowling during World War II. And he was using curriculum to achieve this goal. Finally, the first paper that start to investigate curriculum per se as an interesting phenomenon to study is this paper by Lawrence, where they studied mice. And this was, again, a visual discrimination task. And finally, the same experimental paradigm where they were comparing different presentation protocols from easy to hard to easy, how fast you progress from easy to hard, and just random. It was replicated in humans by Baker and Stanley a few years after the experiment by Lawrence. And this is telling us that this is an extremely multi-species phenomenon. It is also multimodality. We have examples in auditory system and visual system, and also in something that is more complex. We have now, for instance, this nice work by Liu et al. Experiments that are in the same paper cross species, so they are applying the same protocols, in this case in mice and humans. In this case is a auditory discrimination task. And this works also for, well, probably this is not surprising, but it works also for abstract concept, in this case for language learning. So if you teach a kid to learn irregular verbs in English, you will see that curriculum will help. So now the question to me is, okay, well, this is actually another nice experiment and one that I will use. So in this case, Pachler and Moser came up with this simple experiment about distinguishing demons from the old world and demons from the new world. And this is something that is completely made up, but you can see that there are many differences. And actually, this line was supposed to appear later because among the many different features that are present in these images that you observe, the length of the horn is what is distinguishing demons from the old world from demons on the new world. So if I exaggerate this feature and I create demons that are stereotypical with the long horns and short horns, individuals were able to identify the optimal, to distinguish them very well, and this is what you can see here. So in this experiment, they are starting with the exaggerated feature, and they progressively increase up till block 8 to have less stereotypical features. But you can see that even after removing completely the easy example from the training, they perform extremely well. They perform basically 100% with 100% accuracy, despite the other cohort didn't manage. And this doesn't need to be something that is variable, like I can say that length of the horn is a typical variable, but it can be something very subtle, like the hue of the color of the demon. So it is a very general framework. It's trivial that I discuss so much about curriculum because we all experience it in our life, but we don't have yet a grounded theory for that. Okay, so my question is, what about machines? I like to use neural network models as models of learning, and so I want to see what happens in artificial neural networks. And so here the literature is a bit more controversial. The first example using explicitly curriculum is coming from this paper by Benjo et al. In 2009. In this case, they considered different machine learning problems, and they were looking at how curriculum can help. So here is an example. So in this case, you can see the easy example on the top and the hard example on the bottom, and this is a classification task. So you have to distinguish triangles from circles and from square. Okay. Now, in the first case, you have a high contrast and regular shapes. In the second case, you have lower contrast and irregular shapes. And what they show here, where you have error on the vertical axis and epochs before getting access to the full data set on the horizontal axis. So if I give the full data set from the very beginning, I achieve a higher level of error with respect to waiting for 120 epochs and then releasing the full data set and training until it converges. So this is very promising, but I told you it's controversial because then many other people tried to run other experiments with curricula, and that didn't work. And sometimes even the opposite, so hard to easy work better. The question when I started to work on this problem, I was interested in understanding, okay, what is the issue? Why do we see all these different results, et cetera, et cetera? And so I tried a few things over the past years. I will start with a very simple setting, a convex setting, and then I will move to non-convex and humans, and then structured data. And I will be more explicit, but this is the plan for the talk in practice. Okay, so let's start with the convex setting. This is, again, the demons of Fechler and Moser. We said that you have basically the horn that is relevant and all the rest that is irrelevant. I wanted to create a model that is as similar as possible to this one. And I am in a supervised learning problem, so I need a data set. This is my data set. I have data X and label Y. And what is important is I want my X to be composed of two different pieces, one that is relevant and one that is irrelevant for the task, which will act as a confounder. And you can see that I can make the irrelevant part quite salient by increasing the standard deviation of it. So basically, this is just Gaussian clouds, but some Gaussian clouds are more spread out than the others, and this is spoiling my classifier because they see this as a very important feature. And it is a simple binary classification task as the demons of the old world and new world. So basically what I do, I weight the features, and then I will just threshold them, okay? So in a schematic way, this is the model that we have, and this is actually a model that was presented in the paper by Benjamin et al., but they didn't solve it. You have the features, and now what this represents is that I have a teacher, which is basically the rule that I'm trying to infer, which is using only the relevant information. But then I have the student, which is, again, a neural network model, which is using the entire information. So part of the task is to identify what is relevant from what is not relevant. And feel free to stop me at any time. This is, goes without saying. So there are many parameters that matter for this problem, but and I will not go over them in detail. Just briefly, how many relevant features among the total features is an important parameter, as you may expect, and the amount of noise or the saliency of the irrelevant feature is an important parameter. This is not surprising. So the reason why when I read the paper by Benjamin et al., I like the model is that I could solve it. So we have a series of tools that have been introduced this morning, and they are coming from the long tradition of statistical mechanics. And in this case, what I need to do is just play around with the presentation order. So I will consider 3 different protocols. One is curriculum. So I will first take the samples with this variance to be small, and then I will give the variance hard for the irrelevant feature. For the anti-curriculum, I will do the opposite, and for the random, for the no curriculum, I will do just random shuffled data. What I think is interesting is that in this case, the information content is the same. I am giving exactly the same input, I'm just changing the order. So it's not like there is no cheating here. Okay. I told you my classifier is, again, a simple neural network model, a perceptron. What I do, I update it with the gradient descent. So I take the weights. As I receive a new input, I compute the loss, which is in this case a square loss, and I will just update my weights. So if I want to be slightly more precise, given this is the difference between my prediction and the actual label, so my error, I will have update in this form. It doesn't really matter that you look at it too much, but basically this is just the derivative of the losses. There is nothing fancy here. But what is interesting is that now, instead of having to track all these parameters, because there are still many parameters, theory tells me that I can track only 4 parameters. There are these 4 variables here, and actually one is a model setup, so I can also ignore t. I have to track 3 parameters, and they will tell me everything I want to know about this problem. They will tell me what is the loss that I'm making, what it will be the loss that I will commit, so what is the error that we'll make on a new, for example, that has a certain level of saliency in the irrelevant feature, etc., etc. And I can compute the evolution of this system. So again, this is just to tell you that there is a theory behind. I'm happy to talk more about it, but probably this is not the right moment. But I think what interests me is that theory and simulations match. So this is what you see here. And this image is slightly disappointing. At least it was disappointing to me, because after you did the analysis, you arrive here and you see that the accuracy for the curriculum method, which is the one that we want to beat to win, is slightly better than the others. You see that it's learning faster at the beginning, but then there is no real generalization gain. So this is the first not so interesting conclusion, that you have a speed up, which is expected, but no gain in generalization. But this is very different from what we see in animals and humans. So I was pretty disappointed. And my realization is that I needed something that was more complex. In the end, this is just a problem where I have a single basin of attraction. So if I think of my loss, it's something like this, and I will always go down. So it's just about how fast I'm going down. Instead, what I want is something that is non-convex, where I have competing solutions, and then curriculum maybe can help me to navigate this landscape and find the solution that I think is optimal. And so this is what we worked on next. We consider, well, this is what I just described. This is a non-complex landscape, and you have different strategies. And the hope is that the curriculum will lead me to the optimal solution, which is the one that is lower in energy. And this is what we currently have. So this is this convex landscape where I can change things, I can accelerate a bit, but I will always end up in the same position. And interestingly, there is a long literature about the role of overparameterization. So you know that deep neural networks are deep for many reasons, but they are especially particularly big. And this means that this causes the landscape, the experience, to be not that rough. It is a quite convex landscape. There are a few papers showing trivialization. This is what, when we move from non-convex to convex, we call trivialization of the landscape. And they show that, yes, if you overparameterize, you end up to something that is very simple. And so the claim that I'm making here is that one of the reasons why we don't see the benefit of curriculum perhaps is that deep neural network see something like this, and they don't see something as rough as this, where curriculum will matter. Okay, so what we do is consider another model. Again, I like Gaussians because they are easy to analyze. So a model is a mixture of Gaussians. But in this case, I'm mixing my Gaussian in a very specific way. I arrange them to form these 4 clusters. And if you look at the colors, this is an XOR task. So this is, if you want, you can imagine this as being, you have a variable that is context. And well, in this case, you have to rotate it. But something is contextual. So if I am in this semi-plane, I need to apply one rule. If I am in this half of the plane, I should apply the inverse rule. And to solve this, I need an architecture that is slightly more complex. This has 2 layers. Otherwise, we know this from the first crisis of AI that this wouldn't work. And I can apply exactly the same theory. Now I have more parameters than before, but it's exactly the same theory. And I have exactly deterministic ODEs that I can solve. So we did that. And in this case, I can add the parameter which is difficulty, which is how spread out are these Gaussians. So if I take this centroid and I make it as spread out as possible, the overlap will make it impossible to distinguish the different clusters, and so I will not be able to solve the task. I will perform randomly. Okay, so I'm playing again with my 3 different protocols. In this case, I'm increasing the difficulty in the curriculum, and then I keep it stable. The random ordering is just random, and the no curriculum is always hard. There is no easy situation. And then I want you to give you an intuition of why overparameterization will make the problem simpler. So this is a minimally, this is the next one. So okay, this is my situation, my current situation. I have 4 neurons, and what I want them to do, I want them to align to the 4 different clusters. So this means that I am able to distinguish the 4 different clusters, and I'm able to perform the XOR task.
Just a quick question.
Yes.
So when you mean you do this random, you take so the curriculum one is sigma, which is higher and higher, right?
Yes.
And you wait for convergence of the weights every time, or like.
No. In this case, I don't. I present samples in order, and I don't. So this is an online learning protocol. Okay. So I don't train on the data set and then I increase the data set. I train on a specific sample, and then the next sample is going to be slightly more complicated until I get to the end where I see only complicated examples. Okay. So this is a good point. In this case, there is when I talk about time, I'm also talking about data set size. So the longer I train, the more samples I've seen, and they are all different. Okay, So now I'm training with three different hard conditions. So sigma that you see here is the hardest it gets. And you can see that if I take sigma that is small, basically I see that all the methods converge to three different solutions. So these are different simulations starting from a different initial condition. You can see that they all converge equally on these three different solutions. The only difference is that curriculum is a bit faster, but this is what we expected because of the results that we have just seen. As I increase the difficulty, you can see that now you see more of these initial conditions that land at a higher level of the loss. And this is, again, this is the, well, it becomes orange because it's yellow and red. But basically, the two bad protocols lead to worse outcome. And eventually, at this level of difficulty, all these protocols lead to bad outcome, except the curriculum one, which leads to a better level of loss. And finally, there is a difficulty level where the task is just too hard and I will not be able to do anything at all. Another way that is not dynamical to see what is going on is I will just focus at the average performance at the end of my training, and I compare this for the different protocols. And so this is exactly what you have here. On the horizontal axis, you have the difficulty level, and on this plot, you can see the average loss that I reach. And you can see that curriculum is generally lower than the others, but when the task is very easy or very hard, there is no difference anymore. And this is something that you can also see from this plot here. In this case, I'm showing how many of these clusters of these centroids I'm able to correctly identify. And what I want is an algorithm that is able to identify all four of them. And you can see that at the beginning here, there is no big difference. In this, if I instead focus on this level of difficulty, I see that most of my simulation from curriculum are able to land towards recognizing all the different centroids. Okay, and finally, at this level, basically, they are all performing quite badly. They can recognize at most two centroids, which is as bad as random guessing. Okay, so now what happens when I overparameterize the problem? Well, if before the situation was this one, now basically I'm initializing my system with many different directions. So you can imagine this as having a neural network that is more interested about different features by chance. And so if I am in this situation, the probability of landing by chance in good alignment with the centroid that I'm interested in is higher. So this is behind what is called a lottery ticket hypothesis. And it means that it is true that I can solve the problem with only 4 different artificial neurons, but in this case, having more neurons helped me to find this solution by chance. And this is just another way to see this. In this case, the different colors indicate different sizes of the network, and you can see that as I increase the size of the network, my loss becomes lower for a given level of difficulty. Okay, let me skip this slide. So now what I'm claiming here is that when I overparameterize, I'm making the landscape more convex, and therefore it's harder for me to find to have a useful curriculum. And this is exactly what we see here. So I'm taking one fixed level of difficulty, I increase the level of overparameterization, and I look how many of these centroids I'm able to cover. And I can see that for 4 neurons, I'm able to cover all the centroids. As I overparameterize, all the strategies become able to perform well on this task, with some problems for the only hard one, but in general, you have this advantage. And this is a generalization of this idea. in this case, what I'm doing is I'm training for a long number of epochs, which is 10,000, 100,000, and 1 million, providing only the first 1,000 samples easy. And what I want you to see from this plot is that curriculum is helping, especially when you have a small k, while for the others, basically, the impact of curriculum is going down. So as you over-parameterize more and more, basically you don't have any benefit from using curriculum. Okay. So now the question is, okay, how would human perform on this task? And this is basically a variation of the task that Sophia just introduced, which is this random.motion task. But in this case, it's for humans instead of mice. And there is a contextual twitch, it's a contextual modification. So in this case, what you are supposed to do is to look at the motion in these dots, and there is some coherent motion that emerges. But now there is a confounding effect, or there is a contextual variable, which is the fraction of colors that are blue or yellow. So if you have a lot of blue colors, then you have to say left if the points are going up. If there is a majority of yellow color, when they are going up, you should say right. Okay, so this is exactly the same sort of task, but in a different context. And in this case, we considered four different protocols. We have the ascending, which is the curriculum that I just explained. The hard, is only hard level. Random is shuffled, and then we added an additional protocol, which is the bad curriculum. In this case, what we do is we slowly move from one context to the other without caring too much about the difficulty level inside the curriculum. So basically, it is random in difficulty level, but what I'm showing is mostly 100% from one context in the first trial, and as I move towards the different trials, I get to perfect mixing and then complete the opposite context. So it is very hard for a human, because at the beginning they feel like they're doing perfectly well. Then they start to make error, they don't understand, and then the context has completely switched. But if they don't pay attention to what is the context variable, they will just fail. And so, yeah, this is exactly the same task that I was presenting before. Now, color is basically my horizontal axis, and my vertical axis is how coherent is the motion. Color and motion. Okay, so we run this experiment. This is a bit of a painful experiment to participate in, but they did, and what we see is these different outcome. If you are in the ascending condition, you generally perform better than the others. I think what you see here is pretty much coherent to what we will expect. Hard and random. So hard is the second worst, random is the second best, and bad is pretty bad. But I think what is interesting here is that you can see that there is a split in the populations. So what curriculum does is not that magically teaches you how to perform a task, but is pushing you towards the right solution when you struggle to find one. The fact that you have this kind of bimodal distribution of the result is an interesting factor for us. So you can see here that if you take the hard or random condition, basically you have these two modes. In the random is a bit harder to see, but in the hard is very clear. But when you add the curriculum, you are pushing more people towards the upper mode. And when you use the bad curriculum, you are pushing people towards the lower mode. And you can also check what is happening during training. And this is what happens for the ascending condition. In this case, they are rapidly learning. And then as the the task becomes harder and harder because you are progressively giving harder tasks. You can see that the curve is going slightly down, while for the hard and random condition, the curve tends to go up in both cases. And in this case, you can see that there is a separation of the two communities. So at the beginning, they are performing the same, and then you can see there's a clear splitting. And for the bad curriculum, instead, you perform well at the beginning, then you perform badly because you are in the mixing condition, and then you perform very well because now you are very convinced that the task is a simple one, but it's the reverse of what you did at the beginning. What we did here was considering the final performance to cluster individuals and to see how they perform during the training experiment. And in this case, you can see that there are people that get it and people that don't get it. And well, the different protocols basically just modify this histogram here. And in the case of the neural network experiment, this is basically the same quantity. You see a very similar trend. So in this case, you have this going up and down, going up, and then you have this U-shaped performance. Something that I found quite interesting is that what happens in the neural network experiment if you do extremely long training. In this case, we always give the first, I think, 100 trials that are easy, and then we keep training, providing only hard trial. And what you see here is something that is reminiscent of the Eureka effect. So the Eureka effect is something that people have seen in psychology, where few presentation of the easy task allow you to completely understand the problem and solve it, despite the fact that that the problem is much harder. And if I give you only the hard problem, you will not be able to perform. And this is basically what you see here. Eventually, also the other conditions will catch up, except for the bad condition. So if I give you a bad curriculum at the beginning, you will never get it. You will destroy your chances of learning. And I see that we are getting close to the time, but I want to present you a last result, and this is going to be quite quick. In this case, I wanted to study structured data, because one of the answers of why curriculum seems to be useful is, okay, if you have competing solutions, I can lead you towards the right solution. But another motivation can be, well, if there is structure in my data, I can help you to identify this structure. And this is something that actually partially we see also in this XOR model, but in this experiment is clear. So in this case, we consider a model where you have, again, a kind of a perceptron learning. But instead of focusing on a single perception problem, we have a bunch of them. So in this case, you imagine this as having to make different choices. And if you mess up with one choice, you don't understand what happened, you just don't get any reward. Instead, if you get all the choices right, then you get the reward. And the motivation for this was kind of simple, getting closer to experimental protocols where the mouse is in a completely new environment and they don't understand what is going on. And then they have lots of different things that they have to do, even if, well, for us, it may feel like just discriminating whether the grid is going to left or the right. And they have to make all the decisions right in order to get the reward. And then there is no negative reinforcement. I mean, we can introduce negative reinforcement here, but it's not as it's hard to get a gradient in that case. So okay, we have update rules as the one before. This is a bit different because it's not directly gradient based. We can apply the same technique. We have the order parameters. This is great. And the order parameters basically tell us how well we perform. And this follows some deterministic odds. So nothing new. We can solve the problem. This is not surprising. What is kind of interesting is that there is this initial slowdown at the beginning, because at the beginning you just try out things and you don't understand what is going on. And eventually you start to realize that this is the solution. And finally, you convert to the solution, and everybody's happy. As a small result here, we have a speed accuracy trade-off. So if you spend more time learning the task, and by this I mean that you take tasks that are harder at the beginning, then you get a better improvement at the end. So in this case, I'm changing the difficulty of the task, which means how many of these binary classification you have to get correctly. And you can see that this slows down learning, but eventually you get to a higher level of performance. Okay, but why I'm talking about this? Well, because if I take a bunch of these things, I can imagine this as being a series of tasks that are combined together in a compositional way. And I can create a task that looks like this. So in this case, I have all these RL perceptron, this is how we call them, that are primitive subtasks. And then I have a compositional task that put them together. And then I train a student, which is a two-layer neural network, which has to perform well on this task. And we use this as a model for understanding shaping in animal training. So in animal training, you probably know, well, they will not be able to perform the task immediately when you put them on the apparatus. There will be a lot of these shaping protocols where you teach the mouse to stay on the wheel. Then you teach the mouse that they have to stay at fixed, which is, I mean, something that is quite uncomfortable for them. And then they have to learn that there is a task, or they have to learn that eventually they have to lick. Those are all small adaptations that somehow we have to, experimentalists have to teach the mouse. And at the moment, how you do that is kind of a art. No, there is no guideline to do that. Papers usually they don't say much about it. So this is to us is a first step to understand. Okay, why this is useful, which is quite straightforward. But eventually, what we want to do is try to find some recommendation of what is the right ordering of shaping, or what is the right duration of shaping to get more mice to be able to perform on the task. So here there are lots of things that go on. Mouse is at fixed, it knows that there has to know that there is some reward to get. It has to run on the ball. There is a virtual reality environment which is not very natural for them, and it has to collect the cues. In this case, there is a cue accumulation task. Okay, so we compare two different protocols. One is the vanilla protocol. I'm basically putting my mouse on the wheel. I will not have mouse. It will be all synthetic. And the other protocol is that I do pre-training on the different primitives, and then I train all together. Great. So if I train on the primitives first, I can see that I have a behavior that goes like this. So I can predict with my theory how much time it takes to learn every individual primitive, and this is basically what is given by these vertical lines. And then after I learn the primitives, I will just train on the compositional task. And this is characterized by these two time scales. The primitive one is the longest, and it is exponential in the difficulty, which is my T parameter. And then there is this compositional task that becomes kind of negligible after you learn the primitives. And well, this is a validation of the time scale in the simulations. If I do the vanilla thing, it is way more complicated. Eventually, you get again a similar time scale, but you get this additional factor, which is basically telling that depends a lot on how much initially you were aware of these features. So basically, this is the overlap between the features that you want to select and the features that you have by initialization by nature. Well, and this plot again is showing me just that I have a good theory simulation alignment. So the numerical value is given by the it's the circles, and the axes are basically on the circles, which means we are doing quite well. So this is showing us that there is this that shaping speeds up learning, but this is only part of the story. This is what you see here. In this case, we are training with the curriculum in the solid line. You can see that basically at this point, I learned the primitives, which is the first plot, and I learned the context, which is in the second plot. So by time 0.35, I learned everything. In the vanilla protocol, instead, it takes me 4 times longer to get there. But there is something else, which is it makes learning way more robust. So if I add noise in my learning, I can get to situations where if I do curricula, which is basically the right plot, I learn the task. While in the vanilla protocol, I will not be able to learn it because I will question my choices all the time. And I will not get a stable reward signal, which is what I need in order to be able to learn. And there is and there are lots of different variations of this, but I'm out of time. But this connects very much with continual learning problems and multitask learning problems, because now if I learn the right features, I can also readapt them. So it is not just about stability and robustness of learning, but it's also about learning what is useful for me, because if I learn something that is a kind of a mix of features, despite the fact that I may be able to perform well on a task, when I have a variation of the task, I will have to completely change my worldview in order to be able to perform well on the task as well. And so this is the summary. So what I do is I use neural network models. So I'm revisiting connectionist models using modern machine learning theory result. And the idea is we want to have a mathematical theory of learning. I show you that neural network models can be used to understand curricular learning, and that modern neural networks rarely benefit from curriculum because of overparameterization. Small neural networks instead are more, they benefit more, and they have this kind of eureka effect. The experiment with humans gave a similar qualitative behavior as the neural network experiment, and we use the neural network to design some of the products that we use for humans. And finally, curriculum learning can give a stronger speed up in compositional data. And that's it. Those are the people that contribute to this works, and yeah, those are support findings. Okay, thank you.
So we have time for a few questions. No question. So I have at least one, maybe two. So what would you consider doing, like reinforcement learning, or it's totally out of the? Because you talked about this reward, but it's still like reward with some more RNNs.
Yeah. So at the moment, this RL perceptron is a model for reinforcement learning, but it is a weird reinforcement learning paradigm. So in this case, this matches the performance of reinforce, which is one algorithm used in reinforcement learning. However, there is no concept of state or value in this problem. So this is something that we are considering, but we are considering it in a different context. We are not considering this as a for understanding behavior, but more as a machine learning theory problem. But yes, this is a natural extension.
And also, so I know some RNN which try to get more biological, and instead of this gradient descent, they use kind of global gradient descent, using like something could be neurotransmitters, you know. So what do you think about using this? Because what I see, like as a human, when you can learn very fast, also if you are very motivated.
Yes.
would you try? Do you know these models maybe? Would it make sense to add this kind of layer of motivation, or it's too hard?
So we studied fatigue in one paper, okay. And we studied fatigue as but we study in the reverse of what you are suggesting somehow. Okay. So basically, fatigue is something that is telling you, okay, I want to switch to another task. Okay, so and there is some. It's kind of interesting problem because you often are not really okay. There are different theories. One is keeping your brain active consumes energy, so there is some biological need of you to just stop. However, there are experiments with incentives. So you maybe you are working on something and you don't want to work anymore, and I tell you, look, I will give you 1,000 krona if you finish the task, and then you are suddenly more motivated than you were. So this is a bit against this biological, this metabolical cost of associated to fatigue. So the theory that we were implementing was suggesting that fatigue is instead a way that the brain has to avoid starting to overlap previous memories. So it's a kind of a memory consolidation mechanism. Once you are fatigued, actually it means you may be willing to switch to another task instead of continuing the task that you're currently doing. And so
probably a task that you know much more.
Not necessarily. But maybe sometimes, yeah, well, I mean, this is a intrinsic mechanism, but the idea is just you want to avoid forgetting stuff. And so you may switch back to another task because now you feel like you need to do it. And there is some agreement with, this reproduces some of the experimental data. Sure.